This is a chi-square. This X-looking thing is a Greek letter chi, like car. It's C in car, not the C in celery. So that chi-square, and I don't know why they gave it this name, but the guy who developed it said this is what it is. It's a test for agreement or independence. We used to use this a lot for Landsat imagery classification, where you get a signal from a satellite and it bounces back however many wavelengths it's got, and based on the wavelength you say this is a tree, these are trees, or this is grassland, or this is bare ground, rock, whatever. And then you would go to places to check it. So you do ground truth, so that you look at what the image is, or what the satellite says it is, and what is actually is, so that you get a contingency table. This is ground, trees, crops, and there's like a dozen different things. And then we've got ground, trees, and crops. And this is image. And this is actual, call it. And you go to a certain number of spots and you look at what was classified and what it really is. So that if I got ground and it was really ground, it goes in this box. If I got trees, it was really trees. If it was crops, it was really crops. This is the main diagonal of this contingency table. And the errors would be here. If it was ground and I said it was crops, it goes there. If it's crops and I said it was ground, it goes there, and so on. We also did this with LiDAR. And literally the deal was, did you hit something or did you hit the ground? You familiar with LiDAR? They do it all the time now. They send a beam of light down, and of course they do this like there's thousands of them, but you send a beam of light down and it bounces back. And if you hit the top of a tree, it will be a shorter return. And literally these things can detect a millimeter of height difference. So that what you want to know is, what does this look like? Is this really the ground, or is this the top of a tree? So that if you want to measure the height of the tree canopy, you need the height from the top to the bottom. But you got to make sure you got the bottom. So it was, did we hit the bottom or didn't we? Was it really the bottom or wasn't it? So that this is a test to see whether you got it right. And that would be a test of agreement. You can also do it as a test of independence, where this is where things get weird. It was a psychology test. This is used in psychology. And they have two different psychologists assess these people for whatever it is. And this one says they're schizophrenic. This one says they're something else. So you make a table of diagnosis. And it says, are these people in agreement? Do these two psychologists agree? So at the same time, it's a test for agreement. It's a test for independence. Were they independent in their assessments? It's not difficult to do because the computer does it. But it's difficult for some people to get the idea up. This in the My Open Math, go to the very first page. So we're at the very first page, and we've got chi-square here, and this is chi-square data. So we need chi-square data. This is used in drug tests. Does the drug really work? So that I gave the drug to 50 people and I gave a placebo to 50 people. And this is in a double-blind study. These are done so that neither the doctor nor the patient knows what treatment they're receiving. So we've got 50 people getting the drug, 50 people getting the placebo, and the question is, does the drug work? So in this, the drug worked in 30 out of the 50 people that got the drug. It didn't work in 20 of those people. The placebo worked in 22 out of 50, and it didn't work in 28 out of 50. So all we want to know is the placebo effect any different than random, basically. Right? And this depends on the observed values and the expected values. These are the observed values. This is what actually happened. And the expected values we have to calculate in this case. So we've got 50 people in here, in each group, so that if there was no effect, how many people would be in the yes and no category for the drug? The drug has no effect. Got 50 people, say it's half and half. The drug didn't work. So I would expect half of these people in there and another half there. The way this is actually calculated is on that proportion, but you calculate it as this divided by that. It's going to be 50% multiplied times the number in that column. So that this cell is equal to 50 times 52 divided by 100. We expect half to be in there. There's 52 people in there, so 26 would be expected to have responded to the drug if it's just random. The next one is exactly the same calculation, and it's exactly the same value, but it's not always the case. So it's 50, and I'll do it differently, divided by 100, and then multiply it times the 52, and I get 26 again. So this is just how many I expect. So if I've got 48 people in the no group, how many would I expect, if there's no effect of the drug or placebo, how many would I expect there to be in each of the two categories? I'm in the no category, and drug and placebo, if it's 50-50, there should be 24 in each one of these things. And you can calculate it. And the calculation is always the total there times the total there divided by the total number. When you get to different numbers than 50-50 and so forth, it's the same thing, but the calculation is the same setup. You just get different numbers. So the expected is what would happen if these two things had no relation to each other. It's completely independent. The drug doesn't work. So these are the observed values, and these are the expected values. And the test is I take each one of the observed values, subtract the expected value, square it, and then divide by the expected value. And the computer is going to do all of this for you. And part of the problem is the computer is going to do all of it for you. And it just comes up with answers. But here, pick a spot, and I'll just keep it in line with this top part, equals, the first cell is 30, what's in that cell, minus what's in the expected cell. And then square it. And then divide by the expected value. This is observed minus expected squared divided by expected. And the difference, basically this is 30 minus 26. 4 squared is 16, and then divided by 26. So this number is 16 divided by the 26 in the expected cell. And this is pure mechanical, right? And since it's set up that way, you can copy it over and then copy it down, and all the cell references are consistent. So it's 30 minus 26 squared divided by 26. Then 20 minus 24 squared divided by 24. 22 minus 26 squared, which is 16, divided by 26 again. So I get the same number in both of those. And 28 minus 24 divided by 24, we get that number. Right, so it's always positive, and the test layout is observed minus expected squared over expected for each cell. And then we need the sum of these things. And we can get it all together here. So the chi-square value for this test, the test statistic, is 2.56. We don't need a whole bunch of decimals. So 2.56 is the chi-square. We need to compare that to a value in a distribution, and it's in a chi-square distribution. And a chi-square distribution looks like this. And you only used the right tail. There's no possibility of a negative. It's not like a t-value. It could be -2 or +2. It's always positive, so we're using this tail here. And the usual standard is 5%, 0.05 for alpha. To get that, we go to the chi-square distribution. This is equals, and start CHI, and you get all the chi-square statistics, distribution, and so forth. And we've got a number, we're going to a probability, and we're using the right tail, so this is chi.dist.rt. And here's our value, and this requires a degrees of freedom. And the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. There's 2 rows, 2 columns. 2 minus 1 is 1, 2 minus 1 is 1. Multiply 1 and 1, you get 1. And this gives a probability, a tail probability, a p-value of 0.11, basically. All right, so here's the picture, the layout. Our chi-square value is at 0.11. There's 11% probability from the chi-square value up. So that at the 5% level, I cannot reject that these two things are the same. The drug doesn't work. Okay, so I calculate a chi-square using that calculation. I have a degrees of freedom, which is equal to the number of rows minus 1 times the number of columns minus 1. And here I had 2 minus 1 times 2 minus 1. So I have 1 degree of freedom. So I had 2.56 is my chi-square value. Its position, its p-value is in the 11% in the right-hand end. And if I test this at the 0.05 level, I cannot reject the null hypothesis that they're the same. The drug doesn't work. Look back in the file, and this is children and adults, chocolate and vanilla. And the test is there some preference? Do children prefer chocolate or vanilla compared to adults preferring chocolate or vanilla? So here I've got 76 children. And of those 76 children, 47 prefer chocolate and 29 prefer vanilla. I have 114 adults. 53 prefer chocolate, 61 prefer vanilla. And if I add these up, 47 plus 53, there's 100 in the chocolate column and 90 in the vanilla column, and 190 people altogether. So I want to know, is the age independent of the ice cream flavor preference? Do children and adults prefer chocolate and vanilla the same? The only thing you have to do is calculate the expected value. In here, I have 76 out of 190 people. This is equals 76 divided by 190. 4% or 40% are children. How many adults? What percentage of adults? 60. Here's 0.6. Then out of 100 people who prefer chocolate, how many should be children? That's the 40. This is 76 times 100 divided by 190, or 40% are in the child category, 100 prefer chocolate, adult or child, so that 40 is in there. That's the expected number. The mechanical way to think of it is this total times that total divided by the overall total. And this probability, this is a probability distribution. How many are children? 40%. How many are adults? We have a probability distribution. And if we use that probability distribution on 100, we get 40 there. How many, then, are expected to be in the adult and chocolate box, entry, cell, whatever? I've got 100 total. How many are children? 40. So how many are adults? Just exactly. Right, so these calculations are not complicated, but it's not something that is immediately obvious. Here, 40% are in this line, this child line, and 90 is in the vanilla. 0.4, 40% of 90 is hopefully 36. And this is going to be 76 times 100 divided by 190. If you make it mechanical, it's purely that. And here, I can do this by calculation, 114 times 100 divided by 190. Or, I got 36 there, 90 there. How many have got to be in the empty cell? 54, 90 minus 36, 54. It's got to add to 90. 10, 8, 9. This is an actual probability distribution, and it's called a marginal probability distribution because literally it is on the margin of this table. This is a probability distribution for chocolate and vanilla, and it's the marginal probability because it's on the margin. That's why it's called a marginal probability. This is one of the few names that ever make sense in statistics. That's the complicated part, calculating the expected number. Pick a spot. How many degrees of freedom first? 1. 2 minus 1 times 2 minus 1 equals CHI, and we want chi-square dot test. And it gives the actual range and the expected range. This is observed as the actual, and the expected is expected. And all you do is mark the observed, comma, then mark the expected. And I've got these laid out all even up. It doesn't have to be that way. They can be anywhere, either one. And here, this gives me the area in the right tail. It doesn't give me a chi-square value. This one, I have 0.038. It just gives the p-value for this. Here's the chi-square distribution with 1 degree of freedom. And the actual position of my chi-square test value, what was it? 0.038, 0.04. 4% is in the tail. If the alpha level for the test is 5%, here's 0.05, then the chi-square value is in the rejection region. It's further out in the tail than 5%. This does not give you the test value directly, it gives you the result, which is an oversight, I think, on their part, but that's the way they do it. But I'm going to calculate it. The chi-square value equals n observed minus expected squared divided by the expected. Oh, okay. Yes. No, I don't want to accept that. Go away. Raised to the 2. I forgot the 2. So this is 47 minus 40 squared divided by 40. And if I copy that calculation for each cell, all of them are observed minus expected divided by expected. Observed minus expected squared divided by the expected 36. Then I'm going to add these up. Get the sum of all of those things. And there is the actual chi-square value for this test, 4.31. So if I go back to my picture, this is at not that one, this one. The chi-square test value is 4.31. There is a way to recover this. Here, I got 0.04, 0.038 in the right-hand tail. Pick a spot, equals, then CHI, and I have a probability, and I want to go to number, so I'm using chi-square.inv RT. I need the right tail, and there's the probability. Oh, I forgot. Degrees of freedom. 1. And it will give me the actual chi-square value. This is what I don't like about this thing. It goes directly to the result, to the p-value. It skips the test statistic entirely. It's like you did a t-test and it went right to the p-level. But this is the value in the tail, and if my critical area is 5%, this is within that 5%. And so what I'm getting out of my chi-square test function is how much is in the tail. This bit here. And for this one, it was this bit here. All right, so keep that in mind. We're going straight to the result. There's no stops along the way. Here, and I don't know where this is from. This is probably made up. It has level of education. High school, bachelor's, master's, PhD, and marital status. Is there a pattern in marriage and divorce by education level? And education has nothing to do with intelligence. That's been proved so many times that it's almost a cliche. So what should it have to do with marriage status? Here is the observed. 36 out of 234 people had a high school diploma and were unmarried. 36 were married and 9 were divorced. The total with a high school diploma is 81. Each of these is the same. Bachelors, 21 are married or unmarried, 45 married, 9 divorced. Masters, 9 unmarried, 36 married, 3 divorced. Total of 48, 6, 21, 3, and 30. Those are the observed values. We went and got 234 people and asked them their education level and whether they were married, never married, or divorced. This is the expected table. The 25 comes from 72 on this marginal total times 81 here divided by 234. And this is just like before. This is equals 72 out of 234. And we got it set for no decimals. So 31% of the people are unmarried. 59% are married, 10% are divorced, and that should add to 1. So if I've got 31% in the unmarried category, I would expect 31% of each of these values to be in the unmarried cell. So 31% times 81 should be 25. 31% times 75 is 23. 31% times 48 is 15. 31% times 30 is 9. That's the complication in the calculation. How do you get the expected values? All right, so now we can do the test. We've got observed and expected. It's equals CHI SQ dot test. It asks for actual. Just mark all those, comma, expected, and there I have the area in the tail is 0.019. This is where the actual chi-square test value is. If I'm doing this at the 5% level, this is in the tail. I reject that these things are independent. Marital status and education level are not independent. Now what? Which one is it? What cell or cells cause this thing to be significant? Can you tell? Basically, which one has the biggest difference between observed and expected? I'm going to go here, and I'm just going to repeat this table I'll put it down here. I'm going to copy this table. I don't need all of it. And I'm going to put it here. And I don't need any of these numbers. Don't need any numbers at all, for that matter. I just need the table layout. In this cell, I'm going to get the difference between the observed value and the expected value. The difference between 36 and 25. So this is going to be equal to observed 36 minus 25. There's 11 people difference in those. Each of these, I'm going to get the observed minus the expected. And for this, you can do this. 6 minus 9 is minus 3. 9 minus 15 is minus 6. Or you can do it by formula. And since it's set up this way, I can just copy the cells or copy the calculations. So what has the biggest difference between observed and expected? Married, unmarried, high school. Chi-squared tells you these things are different. It doesn't tell you which one.